Okay, so this is an example of of the genre of cross-stick puzzles. So there's all these flat, straight pieces that slot together, and there's a assembled version in the middle and a second copy with the pieces on the outside of that. And it turns out that when you look at this kind of puzzle, there's lots of examples of ones that are on grids, but there's also a whole bunch of different configurations that you can make that work for this kind of puzzle. What's required for a configuration to be a good cross-stick puzzle configuration is that each line segment should be the same length and should have congruent points for where the intersections show up on each one. So there's some good ones. There's two parts of the cross-stick puzzle design. One is finding that geometric configuration. The other part is designing the slots. So there's two simple ways of doing that. One is to have two kinds of slots where there's deep and shallow ones, and they're all going the same way. And the other ones, you have ones that are going up and down, and they're going they have the same depth. And this is what makes it a puzzle, is that some of the two types of slots match each other, and they don't match themselves. So you have to get the right kind of slots in the right place to solve the puzzle. And one thing that you might be interested in finding out is how many kinds of pieces, or how many different pieces can you have given a certain design for the slots in the certain puzzle. And that depends on the number of slots you have, which is represented by the ring in this diagram, 2 through 5, and the legal flipping actions that you can take. And the horizontal flipping comes from the geometry of the puzzle configuration itself. If the pieces are symmetrical, then you can flip it horizontally, otherwise not. And the vertical flipping comes from the type of slot that you chose. So if you have the deeps and shallows, you can't flip that upside down. And if you have the ups and downs, you can flip that one upside down. That gives you the quadrant that you're in this diagram here. And so what we would like is to have a puzzle that has a complete set of unique pieces. That would be the mathematically elegant thing. And so you can look at your configuration and see if it matches one of these numbers here, or you can go backwards and say, I know that I can do a star with any number of sides, but it's going to be the 10-sided, 10-pointed star that is going to be the interesting one, because that will give us this complete set of unique pieces. And the numbers that are in gold in this are ones that I've ended up using in puzzles that I've designed. Sometimes it just doesn't work out. You have a diagram that has 8 pieces on it, and the number that you have is 10, so you just have to throw away 2 of the pieces, which is what was done in the first of the thing that I showed you at the very first slide. And sometimes you might have 12 pieces and you have 6 there, and you can use a double set of the pieces. So let's look at separately what those deep and shallow ones can do and what the up and down ones can do. The deep and shallow pieces, turns out they can only do a certain type of configuration that where, because you have all of the slots going in the same direction, you have a downward facing piece. All of the slots that connect up to that are upward facing pieces. So you have these 2 sets that only connect with each other and not with themselves. And so these are bipartite configurations. And here's a few of them. You saw the grid one in the first slide. And this one is my exchange gift. It's a pretty easy one to solve, and it is a complete set, and it has one of each of the possible combinations of deep and shallow slots there. but lots of configurations aren't bipartite, so we're going to have to figure out something else to do with them. And you can tell that these aren't bipartite because they have triangles in them. If you have one piece that's going down, then the next one is going up, and then the third one would have to be going both down and up, and so you can't do that with those deep and shallow slot pieces. So let's look at what we can do with the up and down slots. That has its own set of issues with what I'm calling the assemblability problem. If you take 3 pieces with one up slot and one down slot, you can stick 2 of them together, and then the third one, when you're trying to put it in, half of it has to come from above and half of it has to come from below, and if the pieces aren't made out of flexible material, then it won't fit. Even though logically, theoretically, you could stick the pieces together. You can't actually physically do it.
One minute left.
Okay, so that has a consequence of having these you always have to have one top piece and one bottom piece, so that this complete set won't work because it only has one piece with all going in the same directions. And so here's a double set, and it would be nice if it worked, but it doesn't actually work. You can't actually make these with it. And so I made this inelegant set that actually makes this figure. And then you have some configurations that are partially bipartite. The inner ones are bipartite, the outer ones aren't, and that you can make up and downs for the outer slots and the deep and shallows for the inner slots, and mix those together, and it actually solves the assemblability problem at the same time. And so those work. This was my G4, G10 exchange gift. And I'll just go through these. This is another one where it only makes these 2 if you use just the deep and shallows, but you can make 8 out of those 10 different things at the bottom row if you use the others. And I will stop there, but there's some other good stuff. Thanks.